Hello friends, in this video I'd like to solve 7 problems from the second round of AGH University Olympiad for high school students, this year edition, current edition. So if you don't know, AGH stands for Akademia Górniczo-Hutnicza. It's one of the best Polish universities located in Kraków. And actually, this Olympiad, better to call it just a competition because the level of difficulty is nowhere near the Polish Mathematical Olympiad. But the second round of this Olympiad took place yesterday, and so I am free to publish my solutions to it, I believe. So yes, let's get to and one more thing. 7 problems are to be solved. First 4 problems are considered to be easier. They are both 10 points each, and last 3 problems are worth 20 points each. To pass to the third and final round, one needs to achieve at least 70 points. Alright, so let's solve it. Problem number 1. Let p be a positive integer. We wish to prove that p squared plus 4 and p squared plus 6 are primes if and only if p equals 5. My hint for this problem: consider all possible values of p modulo 5. Give this problem a try. Okay, so here is my solution. Well, let's go case by case. Case number 1. Well, p is congruent to plus or minus 1 modulo 5. Well, that means that p squared is congruent to 1 modulo 5, and that in turn means that p squared plus 4 is congruent to 0 modulo 5. And now we have a problem. Because that means that 5 divides p squared plus 4, but also p squared plus 4 is definitely greater than 5, because p is an integer, a positive integer. Well, for 1, if p equals 1, then p is not a prime, so we can go from p equals 2 and higher. So that means that p squared plus 4 is not prime, cannot be prime. So that case is covered. Case number 2. P congruent to plus or minus 2 modulo 5. Well, then p squared is congruent to 4 modulo 5. And if we add 6, we get the remainder of 0 modulo 5. Again, that means that p5 divides p squared plus 6, and definitely p squared plus 6 is definitely greater than 5, which means that p squared plus 6 is not prime. And the last case, case number 3 and final, p is congruent to 0 modulo 5, which means, in other words, that 5 divides p. But p is a prime, p should be a prime, and that means that p actually equals 5. It actually equals 5. And let's compute the other values, p squared plus 4 and p squared plus 6. P squared plus 4 is 29 and p squared plus 6 is 31. All of these numbers are primes. It's a prime, this is a prime, this is prime as well. So if p equals 5, then our 3 numbers are primes. And the other way around, if all of our numbers are primes, we have eliminated case number 1, we have eliminated case number 2, so p must be congruent to 0, but p is a prime, so p must be actually equal to 0. So our equivalence holds. That means that for every positive integer p squared plus 4 and p squared plus 6 are primes if and only if, in fact, p equals 5. And that closes our proof. Okay, very nice. Problem number 2. Problem number 2. Let an be 2 times logarithm with base 1 over 10 of the absolute value of 1 minus 2n plus logarithm with base 1/10 of 1 plus 3n for all positive integers n. So we have a some type of sequence. We wish to check if the sequence is monotonic, if it's increasing or decreasing. Here are my hints. Notice the following facts. Logarithm with base between 0 and 1 is strictly decreasing. Well-known fact. And we will also need these two basic laws of logarithms. R times log of x is log of x to the power of r, and log of x plus log of y with the same base is log of product xy. And remember also the general fact that if we compose a decreasing function with an increasing function, the result is decreasing. So give this problem a try, and I will see you in just a minute. Oh, wow, what happened? Okay, so now first I wish to transform my formula for an a little bit. An equals 2 logarithm with base 1/10 of the absolute value of 1 minus 2n in absolute value plus logarithm with base 1 over 10, 1 plus 3 times n. Using these laws of logarithms, which I hinted at, I can write this very expression as 1/10, 1 minus 2n squared absolute value, 1 plus 3n. So this entire thing is argument of my logarithm. And now, since I have a square, I can, and we are dealing with real numbers, we can get rid of this absolute value. So it's logarithm with base 1/10 of, for example, we can write 2n minus 1 squared, 3n plus 1. Very nice. And now let's consider separately this function and then logarithm. Well, notice that function which takes a positive integer and maps it to 2n minus 1 squared times 3n plus 1, it goes to positive real numbers. Well, this function is what? It's increasing. It should be visible that it's increasing because we have a product of two increasing positive functions. So is increasing. Is strictly increasing. Let's write it. It's strictly increasing. Strictly increasing. What about the logarithm? Well, logarithm takes a real positive argument, and logarithm with base 1 over 10 x. Well, since this base is between 0 and 1, this function is strictly decreasing. And now we are just composing a strictly decreasing function with a strictly increasing one, so the result is strictly decreasing function. So our function which takes positive integers and maps them to this is strictly decreasing as well. Decreasing. So our sequence, let's write our answer. Sequence an going from a equals 1 to infinity is strictly decreasing. And that is our answer. Very nice. We are going to our next problem. Problem number 3 from planimetry, geometry. Let ABC be a triangle such that side AB has length of 4, BC has length of 2, and the measure of angle B is 30 degrees. We wish to find the ratio of a circumradius to the inner radius of this triangle. Here are my hints. Use the law of cosines to find the missing third side. And recall that we have these three formulae for the area. Area of a triangle can be written as 1/2 side times sine of angle between these sides. The area can be expressed as the semi-perimeter times in radius. In radius is denoted by lowercase r. And also, the very same area can be denoted by ABC over 4r, capital R. This is circumradius. Warning, the ratio is actually ugly. So give this problem a try. Okay, so here is my attempt. First, what I wish to do is to find, first I have made a drawing. It's not very helpful, but it is what it is. So first, let me find maybe the area of, maybe let's denote on our drawing, AB is 4, so C equals 4, BC is 2, so A equals 2, this side B is not known, and this angle is 30 degrees. Okay, so the area of our triangle ABC, we can find it. It's 1/2, let's write it in each, 1/2 CA times sine of beta. So it's 1/2 4 times 2 times sine of 30 degrees. Sine of 30 degrees is 1/2, so it's just 2. It's just 2. Now, I wish to find the missing side, B, by the law of cosines. By the law of cosines, B squared can be written as C squared plus A squared minus 2CA times cosine of beta. What is C squared? 16. What is A squared? 4. 4, 2. What is cosine of 30 degrees? Square root of 3 over 2. So it's 20 minus 8 times square root of 3, which means, after taking square root, that B equals 2 times square root of 5 minus 2 times square root of 3. Unfortunately, there is probably no way to simplify these roots. Very well. And now let's compare two formulae for area. So the area can be written as A plus B plus C over 2 times in radius, and the very same area of a triangle is ABC over 4R. And now I wish to multiply these two formulae. Let's multiply them, and I have area squared of a triangle equals A plus B plus C times ABC over 8 times in radius over circumradius. And now, if I can write it that the ratio of circumradius to the in radius can be written as ABC, A plus B plus C over 8 times the area squared of our triangle. And now everything is known. So let's compute this ratio by plugging in numbers. A is 2, B is this ugly root, c is 4, and here we have a plus b. A it's 2 plus this ugly root, nested root, I should say, plus c 4 over 8 times area squared. What is the area? Area is 2, so it's over 4. And now let's simplify what we can. Well, what we can simplify? Here is 2, here is 4, so it cancels with this 8. And what else? Here is 2, so it cancels with this 4. We have 2. And also here we have 2, 2, and 4. So it cancels once again. We have 1, 1, and 2. So we don't have the denominator any longer. And we have 5 minus 2 times square root of 3. In the parentheses, 5 minus 2 times square root of 3 plus 2, if I'm not mistaken. Let me take a look at my notes. Actually, it's 1 plus 2, so it's actually plus 3. Plus 3. Now it's good. And now I can multiply this times that, so it's 5 minus 2 times square root of 3 plus 3 times square root of 5 minus 2 times square root of 3. And unfortunately, this is our answer. Capital R over lowercase r is 5 minus 2 times square root of 3 plus 3 times square root of 5 minus 2 times square root of 3. It's our answer. Okay, let's go to our next problem, fourth problem. From calculus, from limit problem, we wish to find all numbers m such that the limit as, pay attention, as n goes to infinity of 3 to the power 3 plus n plus 2 to the power 3 plus 2n over 3 to the power of n plus 2 to the power m squared plus 2n, this limit should be equal 3. Here are my hints. Notice the following facts: that limit of alpha to the power of n is 0, provided that alpha is between -1 and 1. It's a constant number. An actual hint for this problem: try dividing both the numerator and the denominator of our fraction by 4 to the power of n. That should do the trick. So give this problem a try. Okay, so here's my solution. First, this number 3 should be equal to this limit. Very well, and now, first I will write it in this way. Its limit as n goes to infinity. Well, what can we do? 3 to the power 3 plus n, it's 27 times 3 to the power of n. Here we have 8 times 4 to the power of n, all over 3 to the power of n plus 2 to the power m squared times 4 to the power of n. And now, what I wish to do is to take these expressions and divide both of them by 4 to the power of n. And now what happens? Well, now, we have 27, 3 to the power of n over 4 to the power of n. It's 3 over 4 to the power of n plus 8. And here we have 3 over 4 to the power of n plus 2m squared. And now what happens? These green expressions go to 0 rather fast, and we are left with 8 over 2 to the power m squared. So now we know that 8 of that 3 equals 8 over 2 to the power m squared. So in other words, 2 to the power m squared equals 8 over 3. How can we get m squared? By taking binary logarithm on both sides. So it's binary logarithm of 8 over 3. It can be written in a different way. It's binary logarithm of 8 minus binary logarithm of 3. Let's put the left, which is 3 minus binary logarithm of 3. And again, and now m squared equals that. This number is obviously positive. It's obviously positive. So our answer, after taking square root, m can be equal plus or minus square root of 3 minus binary logarithm of 3. And that is our answer. We have two possible values of m. Okay, so it was the last problem worth 10 points. Now we are going to solve harder problems. Problem number 5. From calculus and from stereometry. Three-dimensional geometry, you know. So a right tetrahedron is circumscribed about a sphere of radius r. What is the least possible volume of this tetrahedron? So my hints for this problem: let A be the length of the base of our tetrahedron. And by the way, what do I mean by right tetrahedron? Well, I mean that the apex of this solid, that apex of this tetrahedron, is directly above the centroid of our base, and moreover, in our base we have an equilateral triangle. So right tetrahedron should have an equilateral triangle as its base, and the apex of this figure should be directly above the centroid of this triangle. So let A be the length of the base of our tetrahedron, and let h be the altitude of this figure. Notice the following very important thing: the touch point of the sphere, the touch point of the sphere and of a face of our tetrahedron lies somewhere on the altitude of this face. It will be clear once I do a drawing. Yes, make a good drawing and notice some similar triangles, and try to express a squared in terms of variable h and constant r. And then you should get some function. You should take derivative and find the minimum of this function. So give this problem a try. So as I mentioned, good drawing is very important. Here is my drawing. It's pretty good, I'd say. I like it. Okay, so what's happening? So I have my tetrahedron. I have marked vertices of the equilateral base as ABC, and I have marked the apex as capital S. Moreover, capital I is the in-center of our sphere inscribed in our tetrahedron. And also, since it's a right tetrahedron, this S, if we drop S on the plane ABC, it coincides with the centroid of triangle ABC. Centroid, I mark it by capital G. And this sphere inscribed in our figure touches every face at some point, and I have marked the point of touch with face BCS as capital P. Now, let's see. And as I suggested, let's mark let's mark that we have A as the basis, and we have the altitude of our figure is capital H. So capital H. And you know what? Let's take a look. Here we have R. Here we have R as well. So if H is the entire altitude of our tetrahedron, this segment from S to I, this is H minus R. Must be. Very well. And now let's take a look. We have a bunch of right triangles. First, here we have a right angle. Here we have a right angle. And also, here we have a right angle as well. And now we can notice similar triangles. Namely, triangle SG. Oh, one more thing before we do it. I have marked also the midpoint of segment BC as capital D. So I claim that triangle, which one? IPS is similar, IPS, this triangle, is similar to triangle DGS by angle property of similarity. How do I know that? Because actually the measure of angle IPS equals the measure of angle DGS, it's 90 degrees, and moreover they share the same angle, and these triangles share the same angle at vertex S. Very well. And now let's do one more thing before we continue. I wish to find the length of segment DG. How can we do it? Well, let's take a look. If I draw our base A, B, C, G is the centroid. And it's a well-known fact that for equilateral triangle, the centroid divides CD with ratio 2 to 1. So if I have A here we have A over 2. Well, the entire segment CD by the Pythagorean theorem, it's square root of A squared minus A squared over 4. So it's A square root of 3 over 2. And CG is not CG, but I need GD actually. GD is 1/3 of CD. So it's A square root of 3 over 6. A square root of 3 over 6. This segment right here. Very well. And now I wish to write a proportion which is implied by this similarity. Let's mark it asterisk. By condition asterisk, I can write the following proportionality. Let's take a look. I claim that IP to SI is the same as DG to SD. Why is that? Well, because here we have a shorter leg of right triangle, Here we have hypotenuse of one triangle, and here we have the shorter leg, and here we have the hypotenuse. So this proportion is definitely true. And now let's plug in numbers. IP, it's R. SI is H minus R. DG is A square root of 3 over 6. And finally, what is SD? Well, SD, we can use the Pythagorean theorem to find it. It's square root of H squared plus A square root of 3 over 6 squared by the Pythagorean theorem. Now, I wish to take squares on both sides. We can definitely do it. And now we have R squared H minus R squared equals A square root of 3 over 6 squared over H squared plus A square root of 3 over 6 squared. And actually, I want to invert both sides. So I have H minus R squared equals H squared plus A square root of 3 over 6 squared, A square root of 3 over 6 squared. Now let's expand both sides. On the left hand side we have H squared minus 2HR plus R squared over R squared equals H squared plus, well, if we expand it, it's A squared over 12, and here we have A squared over 12. Now, let's take a look. Here we have R squared over R squared, it's just 1, and here we have this over that, it's also 1. So we can cancel that. And moreover, I can factor out H on the left hand side. So I have H minus 2 times R over R squared equals H squared A squared over 12. Well, we can cancel H and V square. And now what we get, I can multiply and I will get A squared over 12 equals, let me get it right, R squared H times H minus 2R probably. Am I right? Let me take a look. No. Well, once again, you know what, let's do it slowly. Here we have H minus 2R equals, I can multiply by R squared. Wrong color, sorry. Again, wrong color. So I have HR squared, 12HR squared over A squared. And now I have A squared equals 12HR squared over H minus 2R. Is it right? Now it is. Okay. So now I have my formula for A squared. And now we can write our function of volume, volume of our solid in terms of H. So volume as a function of H, it's 1/3 times the area of a base. What is the area of equilateral triangle? It's A squared square root of 3 over 4 times H, the altitude. And now it's A squared square root of 3 over 12. No, actually, for A squared, I wish to put this double asterisk. By double asterisk, this is 1 over 12. A squared is 12HR squared H minus 2R square root of 3 times H. And we can simplify it a little bit. It's R squared square root of 3 𝘋² h minus 2r. So it's our function. And also, let's find its domain. Well, obviously, h must be greater than 2r. So let's write it. We must assume that h is somewhere between 2r and plus infinity, because otherwise our volume would be negative. Cannot happen. And now I wish to minimize my function, so I will do what? I will consider derivative. So volume, derivative of volume, derivative. R squared, square root of 3 is a constant, and now I will use a quotient rule. H minus 2r in the denominator. Derivative of h squared is 2h times h minus 2r minus the derivative of my denominator is just 1. So it's minus h squared. So it's r squared square root of 3. And now what do we have? We have h squared minus 4hr over h minus 2 times r squared. And and now what I wish to do is to factor out h. So we have r squared square root of 3 times h minus 4r h minus 2r squared. Very well. And now I need a new page, so give me a minute. Very well. And now, when is this derivative positive? Well, notice that volume prime h is negative for... When is it negative? Well, it's negative for h less than 4r, so between 2r and 4r. And also, volume prime of h is positive, or what's happening with my tablet? Positive for h from 4r to plus infinity. So that means that our function is first decreasing and then increasing. So at h equals 4r, volume of our tetrahedron attains its minimum. And the question is, what is this minimum? Well, let's write it. Volume when h equals 4r. Let's go back a few lines. So we just have to plug into this formula. It's r squared square root of 3, h squared in the numerator, and 4r in the numerator. And in the denominator we have 4r minus 2r. So it's just 16 over 2. 16 over 2. Let's do it slowly, I don't want to make any mistake. 16r squared over 2r. So it's just 8 square root of 3 times r cubed. And that's our maximum volume. The minimum volume. The least volume, the least possible volume is 8 square root of 3 times r cubed. If I am not mistaken. I hope that I did not make any stupid mistake along the way. Hopefully. And you can also check, we are not asked to do it, but you can also check that if h equals 4r, our right tetrahedron is actually a regular tetrahedron with every edge of the same length. But I leave it to you to show that our tetrahedron is in fact regular. It's in fact regular. Very well. Penultimate problem, problem number 6 from Combinatorics. Let set S have n elements where n is greater than or equal to. We partition this set S into possibly empty sets S1, S2, and S3 at random. Find the probability of the following events. Event A. Exactly one of the subsets S1, S2, S3 is empty. B. Subsets S1, S2, S3 are equinumerous, so they have the same number of elements. And finally, event C. Two fixed in advance elements of S are in different subsets S1, S2, S3. It's a nice problem from Combinatorics. Here are my hints. First, S1, S2, and S3 are distinguishable. So for example, what do I mean by that? For example, if I have configuration 1, 2, 3, this configuration is not the same as S1 equals 1, S2 equals 3, S3 equals 2. They are very different partitions. At least I hope so. That is the intent of the authors. For event B, consider two cases where n is divisible by 3 and where it's not. And finally, for event C, it may be easier first to consider the complement of C. C prime I denote complement by this symbol. So give this problem a try. Okay, so maybe let's start with how many events are possible, the cardinality of our probabilistic space. Well, we have n elements, we have 3 subsets, they can be empty. So first element can be put in one of the 3 sets, second one also in one of the 3 sets, and so on. Clearly 3 to the power of n. Now, what's the cardinality of event A? Cardinality of event A, exactly one of the subsets is empty. So first, we need to choose this empty subset. In how many ways? We choose one. We choose one empty subset. And now we have n elements, and we have to put them in 2 subsets, but they cannot be empty. So the total number of putting n elements in 2 subsets are 2 to the power of n, but we need to subtract 2 possibilities. It cannot happen that they both go to first set or that they all go to the second set. So we have to exclude 2 possibilities. So let's write comments. We choose one empty subset. Then 2 to the power of n is the total number of putting the total number, what's the better word? The total number of putting to n elements into 2 sets, but we have to subtract 2 because we cannot put both every element. We cannot put every element in just one set. So it's the cardinality of our event. And now what's the probability? Probability of event A, it's what's 3 choose 1? It's 3. So it's 3 2 to the power of n minus 2 over 3 to the power of n. And it can be simplified quite a bit. It can be written as 2 2/3 to the power n minus 1 minus 1/3 to the power n minus 1. So it's a pretty nice answer, I'd say. Okay, B. Subsets S1, S2, S3 are equinumerous, so they should have the same number of elements. Well, notice that if 3 does not divide n, then cardinality of B is obviously 0. It's not possible to have the same number of elements. So, for example, if we have k elements in every subset, we have 3k elements in total, so it has to be divisible by 3. But if 3 divides n, then what? The cardinality of B, first, we have 3 subsets. So first we have to choose n over 3 elements for the first subset. In n, choose n over 3 ways. Now we are left with 2n over 3 elements, and we choose another n over 3 elements for the second subset, and what's the rest goes to the last subset. And it can be simplified quite a bit to n factorial over n factorial n over 3 factorial cubed. So what's the probability of our event? Probability of our event B, I will write it using the Iverson bracket. It can be written as n factorial n over 3 factorial cubed divided by the cardinality of omega, which is 3 to the power of n, but provided that 3 divides n. If you don't know it, it's the Iverson bracket. It's either 0 when this formula is false, and it's 1 when this formula is true. So it's our answer of this part. Now for the part number 3, part C. 2 elements fixed in advance should be in different subsets, S1, S2, S3. Okay, so first I wish to consider the complement of my event. So these 2 elements should be together. So let's imagine that we have n elements to be put into sets, and we wish to, for example, we wish that A1, A2 are together. Well, you can view it as having now n-1 elements, because they are bound together. So we have n-1 elements to be put into 3 sets. So the cardinality of C prime is 3 to the power n-1. And now that means, obviously, the cardinality of C itself is 3 to the power of n minus 3 to the power n-1. And what's the probability of this event? Probability of C equals 3 to the power of n minus 3 to the power n-1 over 3 to the power of n. So it's 1 minus 1/3, 2/3. Doesn't depend on n. That's interesting, that this number does not depend on n. So now we have our results. Maybe I will mark them. Here was the result for B. Here is a result for C, and here is a result for A. Very nice problem, I'd say. Not that interesting as the first round, but pretty interesting. And now the last problem from trigonometry. Problem number 7. Let alpha be an angle between 90 degrees and 150 degrees. And it's an angle such that 3 times tangent to the power of 4 of alpha minus 13 tangent squared of alpha plus 4 equals 0. We wish to find cosine of 4 times alpha. So here are my hints. If you let x to be tangent squared of alpha, you can reduce our equation to a quadratic equation, and you can solve it by discriminant, for example. And these two formulae are going to be very helpful. Cosine of 2 times beta is 2 times cosine squared of beta minus 1. And famous identity, cosine squared plus sine squared is always 1. And also you may wish to think what are the values of limit as alpha goes to 90 degrees from the right hand side of tangent, and what is tangent on 150 degrees. So give this problem a try, and I will see you in just a minute. So you know what, maybe let's start with checking these limiting values. Well, what's the limit as alpha goes to 90 degrees from the right side? Tangent alpha. Well, it's pretty easy to see from the graph of tangent. The graph of tangent, it has vertical asymptote at 90 degrees, and it looks something like that. And we see that if we go to 90 degrees from the right hand side, we go to minus infinity. And what's the tangent of 150 degrees? Well, tangent of 150 degrees, it's tangent of 180 minus 30 degrees. So it's minus tangent of 30 degrees, and that's minus square root of 3 over 3. So in other words, now we know that tangent of alpha is somewhere between minus infinity and minus square root of 3 over 3. We will use it. So let's mark it as asterisk. Now, let's take our equation. 3 times tangent to the power of 4 of alpha minus 13 tangent squared of alpha plus 4 equals 0. Well, it's a big quadratic equation. We can solve it by taking discriminant, capital delta. It's minus 13 squared minus 4 times 3 times 4, 169 minus 48, 121, which is 11 squared, which means that tangent of alpha is actually either 13 minus 11 over 2 times 3, well-known quadratic formula, or maybe let's put plus in here, or the second possibility, tangent of alpha equals 13 minus 11 over 2 times 3. And now we can square, tangent squared, because remember that our variable is tangent squared. Tangent to the 4th power is tangent squared squared. So either tangent squared of alpha is 24 over 6 is 4, or tangent squared of alpha is 2 over 6, 1/3. And now we are in the second quadrant, so after taking square root, we must choose minus. So either tangent is -2 or tangent is -√3/3. So because alpha is obtuse angle. So it's negative. Okay, and now, you know what? Now we will use our condition asterisk. We know that tangent is strictly less than -√3/3, so it cannot be equal. Cannot happen by our condition asterisk. So we have only one possibility, namely tangent equals -2, and let's take a look. -2 is definitely in this interval. Well, so now we have tangent. Yes, tangent of alpha equals -2. Actually, I wish to find cosine. So let's take square again. It's 4. And tangent is sine over cosine. So sine squared of alpha is 4 times cosine squared of alpha. And now if I add cosine squared on both sides, I have this. And on the left hand side we have 1. 1 equals 5 cosine squared of alpha. So 1/5 is cosine squared of alpha. Very well. Now let's finally answer our question. We wish to find cosine of 4 times alpha. Cosine of twice some angle, it's 2 times cosine squared of 2 alpha minus 1. And we can do the very same trick again to get this. And now let's plug in 1/5. So 2 times 1/5 minus 1 squared minus 1. So we have 2 times 2/5, 2/5 minus 1 is -3/5 squared minus 1. So we have, what exactly? We have 9 times 2, 18/25 minus 1, minus 6/25. And that is the only answer. Cosine of 4 times alpha is -7/25. And that is it. That was the very last question on our test. As I said, pretty nice problems, not very difficult, way easier than the first round of this Olympiad, this competition, but it's still nice to solve them. Thank you for watching. I hope that you've learned something new, that you enjoyed my video, and I will see you next time. Goodbye.